Now there's another form of the dot product, and that comes from the notion of work. And work is force times distance. And effectively, the force is not always in the same direction as distance. So suppose, and I'm a very bad artist, so I'm just going to draw a block, and there's some sort of force being applied by some unknown force. So the force vector, there's a vector there, it sometimes is not parallel to the direction of movement, and so there's some sort of angle theta, and the distance traveled is going to be along the distance of the surface. And so the other definition of the scalar product is where we will go F dot D equals the magnitude of F, so the magnitude of the force, multiplied by the magnitude of the distance, so the distance that this block has been moved, multiplied by cosine theta. And it's cosine theta because if you have a right triangle, then the adjacent and the hypotenuse are involved with cosine. So cosine theta is the adjacent over the hypotenuse. And if we're looking for the adjacent side, then we multiply both sides by the hypotenuse. So the adjacent side then becomes hypotenuse multiplied by cosine theta, that equals the adjacent. So if we were to examine this situation, because the force is at some angle to the direction of movement, we actually only want the amount of force that's actually in the direction of movement. So that's why we're using the hypotenuse multiplied by cosine theta, which gives us the adjacent side. So the adjacent side of this triangle is this side, which is parallel to the motion. So effectively we've got the hypotenuse, the magnitude of the force, times cosine theta, multiplied by the distance traveled, magnitude of the vector d. So this is the amount of force in the direction of movement multiplied by the actual distance. But we use this form of it, we just leave the cosine theta off to the end of that expression. If we wanted to then find the angle, there are some times where we're given the dot product, we're given the magnitudes, or we're given the vectors at least. We can find the angle between the vectors simply by rearranging this. So we would just divide both sides of this by the magnitude of f multiplied by the magnitude of vector d, and then you'll see that that just equals cosine theta. So this is the formula you would use to find the angle between the two vectors. So there are situations where we will have vectors in component form, and we'll be able to find the dot product or the scalar product by doing this. There are sometimes where we will be given actual geometric vectors with some sort of angle between them, and then we'll use this form of the scalar product to find the dot product. And sometimes, of course, then we'll get this geometric situation and we'll be given the dot product, and we need to find the angle between the vectors, and then we will use this. So just a couple little things to leave you with before I assign the practice questions. One of the things is that the dot product is commutative. So just like we saw with multiplication with scalars and addition of vectors and multiplying a scalar times a vector, etc. Some of the properties are the same between all those things. In this case, the dot product is commutative, meaning that it doesn't matter which order you take them, you still get the same dot product, the same result. If you take the dot product of a vector with itself, you're going to get the magnitude of it squared. The dot product is also distributive, so we can distribute the dot product or the vector and take the dot product with other things inside the brackets, and we can even do that with two sums. If we take vector v plus vector w and we take the dot product with vector x plus vector y, then we would just take the dot product of all of that. So it would be vector v dot vector x plus vector v dot vector y plus vector w dot vector x plus vector w dot vector y. It's important also in the notation that you need to include the dot as opposed to just writing the values side by side like we might in algebra. Okay, so that is about it for parallelism and the scalar product of two vectors. There's a little bit of work that I would like you to take a look at the end of the section, and also take a look at the examples that are in the textbook so that you get a little bit of other understanding or deeper understanding of this concept before we take a look at our examples tomorrow in class. So thanks for watching, and we'll see you in class.